Hello everyone. So in this video, I am going to explain the design and implementation of precision half-wave rectifier as well as full-wave rectifier. Now, precision half-wave rectifier is a circuit which is used to rectify, that is, to convert AC into DC, uh, even for smaller voltages, like say even millivolt signal, microvolt signal can be rectified here, which is not possible by using a simple diode. In the simple diode, we can rectify only the voltages above 0.7 because diode require up to 0.7 volts to conduct. That is the cut-in voltage of the diode. So in this case, even a smaller signal can be rectified. Now, how to design this circuit? I'll tell you. So it's a op-amp based circuit. So I need one op-amp. So I go to uh, op-amp here, analog option, analog virtual. There is a 3T virtual, op-amp 3 terminal virtual. I'll place it over here. I need resistors. So I'll go to basic. So I bring some resistor here. So I'll place it over here. One more, and one more over here. Then I need a diode, so which is available under the diode category. Diode. Okay, you can go with diode virtual also. That is enough. So I'll bring this diode. I'll place it over here. I need two diodes. Okay. Then I need ground, which is available in the source. Okay. I'll place it. Some three ground components. One function generator is required. I'll place it over here. One oscilloscope is required to observe the waveform. I'll place it here. I'll start my connection. So this is connected to this resistor. Other end to the inverted terminal. This is connect. I'll reverse it so that you can place it anyways, no problem. But these two diodes should be in the same direction. I'll go with this. This to the inverting terminal. Same. So basically inverting amplifier, but with some additional diodes to rectification purpose, precision rectification purpose. I'll place it this. I'll rotate this. Okay. The positive terminal to the ground through the resistor. Fine. We'll connect this to the ground. Okay. I place one connector in the output to observe the waveform or to representation the waveform output. I name it as say V out. I connect this to the output. I use both the channels of this oscilloscope. Okay, this is connected to the ground. This I will connect to my input side. I want to observe both the waveforms. This I'll connect to the output. Let me change the color of the output because to differentiate input and the output, I'll change the color of the output, the white color I choose. Okay, now I'll set the input here. Frequency as say some 1 kHz and peak to peak voltage of say 1 volt I will consider. We can apply 0.5 even less than 0.5 also, no problem. 1 volt peak to peak. Okay, now let me save this project. Precision of a rectifier. Let me save it. I'll go to the analysis. In that I choose interactive simulation. Okay, I'll run it. Let me check the output over here. Okay, something I'm getting. I'll change the timing durations. I'll change the amplitude levels knob here. I'll make it 1 volt. When the output also, I'll make it one note. Just look at this. Just look at this. I'm getting only the negative half cycle. That means I stop the simulation so that I can observe it clearly. During the positive half cycle, it will conduct and represent it as negative half cycle because of the inverted terminal over here. And during negative half cycle, I'm getting nothing. That means the negative half cycle is flipped. And if you want to change this, now I want to represent only the positive half cycles. In that case, you just have to change the direction of these two diodes. So that I think you can do yourself. Now I will convert this same circuit into the full wave rectifier. So for that, I'll remove this connection because I have to include one more circuit, that is a full wave summer circuit. I'm very sorry, it's a summer circuit. So I need to include some adder circuit over here, which I will do it now. Okay, I need one op amp. I'll copy the same thing. I'll paste it over here. I need a few resistors for adder circuit. I'll paste it over here. One more, and in one more in the feedback path. Okay, I'll connect this output. I'll remove this. I'll place it somewhere here so that I can connect it later to the output. This I will connect to this point, to the inverting terminal. This also I connect to the inverting terminal. This I will connect to the input. You have to apply an input there. This to the inverting terminal again. This the output of the op amp. The positive terminal is connected to the ground. Okay, I need again two channels. I'll start the common point of this. I'll connect this to the ground. This is connected to the input. This is to the output. So I'll connect this to the output first. Then I'll connect this to the output of the adder circuit. Again, I'll change the color of this output to the white so that I can differentiate the input and the output. Now, again, if I run it, the simulation, see this. Before that, a small mistake I did. I have to make a small correction. This resistor should have the value equal to 500 ohm, half of the other value resistors. All other are having 1 kilo ohm, and this should be half of that. Now I'll check the output. Yes, I'm getting the output. Just look at this. I'll stop the simulation to check the output waveform clearly. Just look at this. For both the half cycles, I'm converted into the positive half cycles. That is the full wave rectification output for a full wave rectifier. So if you want to change the gain of the output signal, you can always change that by changing the value of this particular resistor in the adder circuit. So this is precision half wave rectifier as well as precision full wave rectifier implementation, which is used to convert AC into DC for even for smaller signals. Thank you for watching this video.